So now we're going to continue talking about reactions of alkynes, and another reaction that alkynes do is we can convert them into alkenes, right? And if you know your alkene stereochemistry, you can have a cis alkene or a trans alkene. So Lindlar's catalyst, if I use that and I treat the alkyne with hydrogen gas in the presence of Lindlar's catalyst, this is Lindlar's catalyst over here, where it's just a heterogeneous palladium on calcium carbonate catalyst, and it has some lead and then quinoline to make up the catalyst mixture, right? And so if I do this, I get a cis alkene when I react an alkyne with Lindlar's catalyst and hydrogen gas. All right, if I react an alkyne in the presence of ammonia and lithium, then I can get a trans alkene. You can imagine that this is very useful, right? If you're doing a total synthesis or you need to convert an alkyne into an alkene and you need it with specific stereochemistry, then it matters which transformation you use. So the alkyne, if I treat it with lithium and ammonia, it gives me a trans alkene, right? And so how do I remember which one does which, right? And it's fairly made up of fairly simple mnemonic, LCAT, right? Right. To remember this is little children always tripping. I know it sounds crazy, but it'll help you remember. Mnemonics are very effective at helping you remember certain things, committing them to your long-term memory, right? So this mnemonic for alkyne reduction, LCAT, little children always tripping. What does that mean? It means if I use Lindlar's, I get a cis alkene. If I use ammonia, I get a trans alkene. So LCAT, Lindlar's cis, ammonia trans, right? Little children always tripping. That mnemonic will help you when it's time to remember what does what when you see this reaction on the test. All right. Another reaction that alkynes undergo is I can convert alkynes into alkanes. Right. I can take that triple bond and I can reduce it all the way down to nothing, right, to a single bond, just using hydrogen and palladium on carbon. The exact same reaction that the alkene can undergo, right? So if I don't use a specialized catalyst like Lindlar's catalyst or a specialized set of reagents like lithium and ammonia, I just treat this with palladium on carbon, it actually reduces that triple bond all the way down to a single bond. The final component of the alkyne reactivity that we're going to talk about is converting it into what we call an acetylide anion, right? The acetylide is just a common name for an alkyne, right? So if I take that alkyne and I treat it with a strong base, I get an acetylide anion. The pKa of the acetylynic proton is about 25, right? That's not super low, but it's not so high that it can't be removed by a strong base. And the reason that you can do that is because the conjugate base, the acetylide anion, is stabilized through the hybridization state of the carbon, the sp carbon. That sp hybridized carbon is highly electronegative, and so that charge that's on the carbon after you do proton transfer with the base, the charges are very stable. All right. So that this is again simply proton transfer. So what happens? The base comes in and attacks the proton, and then in doing so, right, I'm able to take that proton off, and I get the acetylene anion plus NH3, which is shown here. Right. So anytime I have a alkyne I put in the presence of a strong base, I get proton transfer because that proton is not highly acidic, but it is acidic in the presence of a strong enough base. So what do we use the acetylene or the acetylide anion for? Right? It can be a nucleophile or a base depending on the reaction conditions. So if I take the acetylide anion and I react it with either a methyl carbon or a primary carbon, what I'm going to get is substitution, right? So you can see here what happens, right? I have a methyl bromide. You can see the dipole is polarized, so this is my electrophile. The acetylide anion is my nucleophile, right? That means that dipole means that the carbon is partially positive and the bromine is partially negative. So in this case, the acetylide anion is going to attack that carbon, right? So here are my arrows. I have an arrow coming from the acetylide anion to carbon, and then I break the carbon-bromine bond so that I form a new carbon-carbon bond here in the product between the CH3 from the methyl bromide and the acetylide anion, right? So you can see that here. This is what we call a SN2 type substitution, okay? And so the acetylide anion, if you want to remember this, it acts as a nucleophile if it's reacted with a primary or methyl electrophile, right? And then when that happens, you do substitution, okay? Now let's look at another scenario, right? The acetylide anion here, and now it's in the presence of a secondary alkyl halide or a secondary substrate, right? This, it doesn't do substitution, right? What it does is elimination. So let's look at what happens. So now I have an arrow coming from here to here, right? I have an arrow coming from here to here where I break the carbon-hydrogen bond. Those electrons are going to be used to make a pi bond in the product. And then the chlorine is my leaving group in this case. And so this does an elimination. And if you remember, eliminations always give you multiple bonds in the product. You're either going to get a double bond or a triple bond in the product. And so this cyclohexene ring here is my elimination product. And then the proton transfer happened between the hydrogen and the acetylide anion. That's shown here, and then chlorine is my leaving group. So the acetylide anion, if you put it in the presence of a secondary or tertiary electrophile, is going to do elimination, right? So again, how do we remember this? Well, here's a mnemonic for you to remember, right? 1 sausage, 2 or 3 eggs, right? 1 S, 2, 3 E. 1 sausage, 2 or 3 eggs. What that means, the 1 stands for primary. So primary, you get substitution. Secondary or tertiary, you get elimination, right? So if I react the acetylide anion with a primary electrophile, I'm going to get substitution. If I react it with a secondary or a tertiary electrophile, I'm going to get elimination. So 1 sausage, 2 or 3 eggs. Okay, hopefully that'll help you to remember that. Those, again, mnemonics are great ways to put things in your long-term memory. Okay, store it way deep down in there so you'll never forget it. All right, so here's a recap of what we talked about, right? So we talked about naming alkynes, right? And we said they follow the same IUPAC rules for nomenclature as alkanes and alkenes, right? And we talked about the main method for synthesizing alkynes being a double elimination. You can do hydroboration on alkynes, or you can do mercury catalyzed hydration on alkynes. And when you do that, you get the enol form, which then tautomerizes, right? And you can reduce alkynes to cis alkenes using Lindlar's catalyst, or you can reduce them to trans alkenes using ammonia, right? Or you can reduce them all the way down to the alkane using hydrogenation, okay? And then you can deprotonate the alkyne and convert it into the acetylide anion, which can then be used as either a base or a nucleophile, depending on what type of electrophile you use. All right, so I hope this helps. And if you have any questions, you can always shoot me an email. Thanks.